Hello friends, today I'm going to solve LeetCode problem number 129, sum root to leaf numbers. In this problem, we are given the root of a binary tree and each of the node consists of values starting from 0 to 9 only, and we have a root to leaf path, and for each of these root to leaf path, if we represent the path in the form of number, that is for example, a root to leaf path from 1 to 2 to 3 represents a number 1 to 3. Then what we need to do is for all the root to leaf paths, we get a number, and then what we do is we add all of those numbers and return the value of that number. So let's look at this example here. In this example, we have the root 1, and we know 2 is a leaf node because it doesn't have both left and right children. Also 3 is a root leaf node. So we have two root to leaf path. One is from 1 to 2 and the another one is from 1 to 3. So from 1 to 2 we have the root to leaf number 12, and from 1 to 3 we have root to leaf number 13. So when we add both of those numbers 12 and 13, what we get is equals to 25. So that's our result here. In this case we have 3 leaves, which means that we will have 3 root to leaf paths. So one path is 495, so that would be a number 495. Another one is 491, so we have next 491. All right, and next one is 40, so that's 40, and we take the sum of all of these three numbers and the resulting sum is equals to 1026. So that's what we need to do. So now we understand the problem. Let's see how we could solve this problem. So if we look at these numbers, what's happening here is we are starting from the root and we are going each depth, right? We are going each depth. So from 4 we went to 9, from 9 we went to 5, and then since it is a leaf node we constructed a number out of that, and that number would be added to the next leaf to root node. So what we'll do is we'll add this to our result value, and then now we go backtrack and we go towards its next child, which is 1, and that would create a new number, that is 491, and then we add that to our result, which had the value 495, and we get the result of these two sum in our result. And the next case, what we do is now we backtrack from 1 to 9 and from 9 to 4, and then we go to its another child, which is 0, and then since it is a leaf node we get the number 40, and then we add to our resulting sum, and that will give us our final output. So that's what we will be doing. So we'll be using depth first search in this solution. So let's start coding our solution using the depth first search. Before that, let's also look at the constraints. So what are the constraints? The number of nodes in the tree is in the range from 1 to 1000, which means that there is no empty node, so we do not need to check for an edge case where root is null, so we don't need that. However, we could still do that. So what we will check is if root is null. So if not root, then return 0, because there is no number, so we are going to return a 0. But since the range is from 1 to 1000, we won't encounter this. However, it's good to have the edge cases in our functions. And next is the value ranges from 0 to 9. All right, and then depth will not exceed 10. Okay, so now we know that depth will not exceed 10, and the range of the values, we can now construct our depth first search. So what are we going to do is let the fs equals to function, and for depth first search we will need the root that we are currently at, and also since we are constructing the number from root node to its leaf node, so from root to leaf node we will also need to keep track of the path that we are following. So basically we will be keeping track of these numbers. So we will have to pass two arguments, that is the node that we are currently at and the number root to leaf numbers we have encountered so far. And now here we are going to check for the edge cases. If we have reached our leaf node, that is if we have reached our leaf node, would mean that it doesn't have left and right children. So if not node left and not node right, that would mean that we have reached the end. So let's create our resulting integers. So in that case we will add to our result the number, but since our number will be a string, we need to parse it into an integer. So we parse it into an integer. If not, then what we need to do is we keep on going to each of its depth. So we check if node left is present, then we go towards the left node and node dot left, and we add the value to our num. So we update the value of our num. So okay, what we can do here is num plus equals to node value here, so that we will just pass our num here. And then similarly, if in case node right is present, then we'll pass df as the right node and the num. So num would be the path that we have encountered so far, and when we'll call our dfs function, we'll pass our root node and an empty string, and then finally we are going to return our result. So let's awesome. So talking about the time complexity, since we are going to each of the node towards both the left node and right node and traversing each of the node in the tree, that is the time complexity becomes O of n and the space complexity is constant.